Hello everyone. Hydraulic structures are essential for dissipating energy in open channel flows. The hydraulic jump in particular helps protect downstream structures by reducing flow energy. While design is traditionally based on empirical equations and experiments, understanding the detailed behavior remains a challenge. In this video we will use Ansys FreeFlow to analyze this type of application. Let's start by looking at the model setup. Open Ansys FreeFlow and create a new project in the appropriate folder. Under the Model section, only two options are enabled as shown here. In the first one, you can select the variables to be computed, so make sure to enable the fluid force. Under the Physics section, make sure the gravity vector is defined in the correct direction. For this application, the thermal model is not used, since the flow is isothermal. However, it can be enabled if you are dealing with two or more water streams at different temperatures. The fluid properties are set to their default values. You can review the parameters required for each material for both fluids and solids depending on your application. And then import the geometries by right-clicking on Geometries and Import Wall. Remember that the geometries must be provided as STL files. You can import the entire assembly as a single file or load different sections separately, as shown on the left-hand side. You must also create the inlet and outlet sections for the flow. For each geometry, you can adjust the transparency level, which helps visualize the flow inside the domain. Another important aspect is the triangle size assigned to each geometry, which plays a role similar to mesh and affects the accuracy of the fluid force calculations. In the SPH options, I'm using the default setup. Some important parameters to consider are the solver, the turbulence model, and the SPH element size. Keep in mind that the smaller the element size, the higher the number of particles and the longer the simulation time. The goal of the SPH method is to achieve a realistic representation of the flow while maintaining a reasonable computational cost. In the Solve section, you define the total simulation time, the time step, and the hardware option, either CPUs or GPUs. Once everything is set, simply click on Start to run the simulation. Once the simulation is finished, we can check the processing time. In this case, the last value is equivalent to 1.42 hours. We can also create a user process to visualize the water surface. Check the setup and adjust the transparency as needed. Now, let's look at the animation. First, we observe a transient stage where the flow develops and interacts with the structure. Let's switch to a front view and adjust the camera to get a better framing. When transparency is enabled, the motion of the bubbles become visible, as well as the roller associated with the hydraulic jump. And finally, you can create two additional user processes to define measurement regions for flow velocity and water depth at the inlet and outlet. This allows the calculation of the flow numbers. The results can be exported and further processed using external tools such as Excel. To obtain more stable values, the data was evaluated over the time interval between 20 and 30 seconds. This way, the fraud numbers can be calculated with reliability. And that's all for today. Thanks for watching.